Okay, is that clear? All right, thanks for notifying me about the questions on the chat. I think it was blocked by some other window. Okay, right. So now let's talk about how do we actually form the matrix entries and the right-hand sides. And the first about the matrix. Okay, so the matrix, every matrix element involves an integral. Involves an integral from 0 to 1, the derivative of 1. Let's see. Okay, yeah, the derivative of one basis function times the derivative of another basis function. So that is my Aij. So the question is, how do we compute that? All right. Okay, so I'm first going to talk about how do we compute that for our particular case when we have the basis functions being the head functions. Okay, and again, in different finite element methods, you may have different constraints. Therefore, you have a different set of basis functions. For example, if you constrain your function to be, instead of piecewise linear, you try to do piecewise quadratic, then these basis functions are not going to be all linear. Some of them are linear, some of them are quadratic. But let's just stick to our linear case. So we have, let's say, x and fees, okay? And I have let's say I have a phi I that's like that, okay? So this is my phi I, okay? Switch to another color. I have a phi j that's like that. It's bad drawing because they all should go to the value of 1. Okay. So basically, every phi is going to have the value of 1 at one particular grid point and 0 at all other grid points, right? And again, in the finite element vocabulary, that's called a nodal basis function. It's also, you can visualize it as the head functions. All right, now you have this kind of basis functions. If I'm looking at these two particular phi i's and phi j's, what do you think is Aij? What is Aij in this particular case? Just a look at the integral. Okay, anybody answer me? Yeah, 0, right? Because it is 0, because if you look at the derivatives of the function, let me use red to outline the region where phi I has a non-zero derivative. It's this, right? This is the region where phi I has non-zero derivative. And what is the region that phi j has non-zero derivative? It is in this region. They have no overlap, right? So that means, what does that mean? That means for most of I and j, as long as there are no, if their nodes are far away, so that the neighboring element has no overlap, then the Aij is equal to 0, right? So actually, even if there are two elements away, right? If there are 2 elements away, then phi I is going to be like that, phi j is going to be like that, right? So this is I plus 1, and this is I plus 2. So if I plus 2 equal to j, even in this case, right, this is the red, and this is the non-zero region, and this is the blue, this is the non-zero region, I have no overlap. So even if they are 2 apart, my Aij is going to be 0. So actually, this is I plus 2 for less or equal to j. It's always the case, right? So Aij would actually mostly be equal to 0. So if you actually look into the matrix, you can already see the sparsity structure. I don't know about Aii yet, so it's a question mark. When I and J are one element, one node apart, I also don't know. But as soon as they are two elements apart, two nodes apart, I know they are 0. So it's going to be 0 all the way. Okay. Again, on the diagonal, I don't know. On one element shifted, I also don't know. But as soon as I have two elements shifted, I know it's a 0, right? So basically, you have three diagonals. You have a tri-diagonal matrix. You have three diagonal bands that could be non-zero. Away from these three diagonal bands, all the Aij's are 0, exactly for the reason that the basis functions don't even overlap if they are two nodes apart or more. All right? So we only need to focus on the case where the elements are when the basis functions are either I equal to j or I and j are only one node apart. Okay, so let's actually figure out the first case first. First case is well, the 0th case is already if I minus j absolute value greater than 1, then Aij is equal to 0. Okay. The second case, I equal to j. What happens is Aii, that's the diagonal of the matrix, it is equal to the derivative squared integrated. Okay, so let's figure out for finite element, what is this? And I'm going to be doing something actually I don't think I've ever done before. That is, I'm going to allow my grid spacing to be completely non-uniform. Okay, so I'm going to say I'm going to set my elements to be anything. So I'm not going to restrict my elements to have a fixed delta x. Rather, I'm going to set my ith basis function to be centered at xi. And it diminished to 0 at xi minus 1 and xi